Yes, yes.
I would like, first of all, to thank the Traffic Flow Theory and Characteristics Committee for giving me the opportunity to give this webinar. And I also would like to thank Mehad Saberi for his efforts in enabling technically and otherwise this webinar. I must say that it's the first time I actually giving a webinar. It's a bit of a strange feeling to talk just to a screen and knowing that there are a few people around the world listening. So it's a new experience. As mentioned already, the presentation is about freeway traffic control, past, present, and future. I mean, first of all, freeway, I will sometimes in some slides talk, or in my speech talk about motorway, which is the European word for freeway, so the two are synonyms. This presentation will reflect a lot of work that has been done in the past. Mehad, there's a sound, you say?
Yeah, there is. I actually hear you. Just somebody asked if there is a sound. Yes, I think. Does anyone else have a sound problem? I guess everyone is hearing, right? If you hear, please say yes in the chat box.
Okay, meanwhile, I will go on.
Okay, so yes.
Okay, it seems it's okay.
I will take care of the chat box, Markos, so don't get interrupted with that until the end of the presentation.
Okay, thank you very much. So I was telling that in this presentation there will be also a reference to several results, research results, and also implementation results that we have had over the decades. And of course, this is not all one man's work. And I have to thank all my collaborators and colleagues over the years who have substantially contributed to some of the results that I will be presenting. Now, oops, that was not correct. Let's do it like this. To start with an introduction, we all know that freeways, motorways were originally conceived to provide virtually unlimited mobility to road users. But as you can see in this photograph, I mean, this is actually from Australia, but it's the same in virtually all parts of the world. During the peak period, we have motorways that are highly congested and work at very low efficiency. And this is indeed, I would say, a shame for our technological civilization, because we were thinking that we are doing great in technology, but this is a problem that we still have to address. Just an initial fact that we will need to better understand some of the facts that will follow. You see here on this slide a traffic network. It can be a traffic network of any kind, which receives demands from different origins. And these demands are actually vehicles that cross different parts of the network and then reach their destinations and form the exit flows. We apply control actions to such a network, trying to minimize the total time spent in the network by all the vehicles in the network. And it's very easy to understand and also to prove that if we make the assumption that is not fully correct, but if we make the assumption that the demands are independent of the control actions, then we will minimize the total time spent, or we will reduce the total time spent if we are able to maximize the early exit flows. Because if people can exit earlier, then they will have spent less time in the system. So anything that blocks exit flows, or anything that blocks exit flows, is bad for the system, and anything that deblocks or increases exit flows is good for the system efficiency and for the travel times. Now, it's, I think, helpful to look at some other kinds of systems just to get some comparison. If we consider simple queuing systems like a check-in queue at the airport when you go to check-in, and the demand is higher than capacity because there are more customers than counters, then you have to queue, and this means that you have some delays. The point here is that the capacity of the system does not depend on the length of the queue. So the queue is there, it gives delays for the customers, but it doesn't mean that the capacity is affected by the delay, by the queuing. There are other kinds of systems like water systems where things are completely different. If you have more demand, more inflow to a network of water network, then you have higher water level in the network, queuing, but this gives rise to a higher pressure and higher outflow. And in fact, under higher demands and higher queuing, you get an increased outflow, which means that the capacity of the system is influenced positively, it increases with increased queuing, which is different than the simple queuing system. Now, what happens with traffic networks? Well, traffic networks are different than both of those two kinds of networks because the congestion degrades the infrastructure capacity. Now, what are the reasons for that we will see in a few minutes. But if we take this as a fact, then at the start of the peak period, you may have actually demand at the local level, some links of the network that exceeds the local capacity. And in this case, the local congestion degrades the local capacity. This leads, of course, to an accelerated increase of congestion, which means further capacity degradation, which means further accelerated increase of congestion. And so we get a vicious cycle that eventually leads to a generalized network congestion over big parts of the network. Although, if you look at the actual demand, or if you look at the traffic flow that is actually served, I mean, it's much less than the nominal network capacity. That is because the network is degraded, and so the traffic that can be served is much less than the capacity. This is an illustration of what I was telling. It happens to be the Ile-de-France expressway network around Paris. So you see Paris and the Boulevard Périphérique around it, and then secondary another motorways. So the image that you see was taken on 12th January 2011 at 8:14 a.m. It's the morning peak hour. It was taken for a day where there was no accident or incident before this time. So the congestion is really a recurrent congestion. There is no implication of incident here. And this means, of course, the red color is congestion, and you can imagine that the network does not perform as it should during nominal capacity. And this happens, of course, not just here, but in virtually any network around the world. So, in conclusion, the generalized motorway congestion that we experience daily is not only due to high demand. Of course, it is triggered by high demand, but it is then sustained and maintained due to the degradation of the infrastructure capacity. And in fact, when our motorway networks are congested, this means that we have a very expensive infrastructure, expensive to build, expensive to maintain, which is ironically not fully available at the only time it is actually needed, which is at the peak periods. So off-peak periods, we don't need it anyhow because we don't have the demand, and then during the peak periods, we don't have it because of the degradation. And so the goal is to operate motorway networks optimally as a controllable system. Now, to advance here, we need to ask the question, what are the specific reasons for the degradation that we mentioned before in the case of motorway networks? Well, as you know, usually bottlenecks are the origin of congestion, And a bottleneck can be defined simply by saying that it's a location where the capacity upstream is higher than the capacity downstream. And the bottlenecks are candidates for congestion, and we have bottlenecks, for example, due to on-ramps merging, or due to geometrical reasons, lane drop, grades, curvature, tunnel, bridge, and so on. Or a weaving section can have less capacity than another kind of section, or speed limits, and so on. So all these are reasons why we could have a bottleneck. Now, what happens at the bottleneck? We have two main reasons for the infrastructure degradation. The first reason is what we call capacity drop. Consider here on the slide a bottleneck, which seems to be a lane drop bottleneck, but it can be any kind of bottleneck. It doesn't need to be lane drop. So we have an inflow entering, and if the inflow is higher than the downstream capacity, which is essentially the bottleneck capacity, then it will go through, and there will be nothing spectacular happening. And if you see the diagram below, the fundamental diagram, flow versus density, we are talking about operating on the left-hand side of the curve, which means that this can happen up to the point where we reach the downstream capacity. When we reach that, then the bottleneck is activated, or when we exceed that, the bottleneck is activated, a congestion is formed, the tail of the congestion moves upstream, and the outflow, as you see in the fundamental diagram, the outflow drops at the area of the red crosses where the system now will operate, and this difference between the pre-breakdown capacity and the after-breakdown capacity is called capacity drop. Although the reasons for capacity drop are not yet fully understood, there are a lot of people, including me, who believe that a major reason for that is the fact that vehicles need to accelerate at the head of the congestion from lower speed within the congestion to higher speed downstream of the congestion. And due to this acceleration, we have the lower flow. So in any case, the capacity drop marks a significant, the numbers that have been reported range from 5%, 10, 20, 25% capacity drop. So this means that the infrastructure is actually degraded, because on our mainstream we now have whatever percentage, 10, 20% of flow less, of capacity less than before congestion. So this is the first reason. The second reason has to do with off-ramps. The congestion that has formed will propagate upstream, its tail will propagate upstream, and will start covering off-ramps. So every time it covers an off-ramp, the flow of the off-ramp will be reduced, because the flow in the congestion is less than upstream of the congestion. And so by what we said in the introduction, if the off-ramp flow is reduced, then the system, of course, will be degraded. In this case, simply because vehicles and drivers who are bound for off-ramps, who are not actually pass the bottleneck, they are not interested to pass the active bottleneck, they would exit before. But because of the extent of the congestion, they are also trapped in the congestion, they also experience delay, and in fact, they also contribute to an increase of the congestion, an accelerated increase of the congestion. And this happens every time an additional off-ramp is covered. And as you probably know, such congestions can be long, quite many kilometers, and can cover many off-ramps. We have seen that also in the image of Ile-de-France network. Now, I think it is important to have in mind an control loop, an automatic control loop, which in our case, of course, applies to Freeway. So as you see on the diagram, there is a process under control. The process in our case is the motorway traffic. there are some inputs enabled via actuators. Actuators can be traffic signals, can be variable method signs, and anything that allows us to take influence on the behavior of the process. But the process behavior is also influenced by other quantities that we call disturbances, which are not in our hands to modify, to change. These can be, for example, it can be the demand itself, the routing of drivers, it can be the environmental conditions, it can be incidents, and so on. Now, on the right-hand side, we have sensors, which are used to collect real-time measurements from the system. And these real-time measurements from the system, and perhaps also for some disturbances, are conveyed to a computer system. So you see the line, the horizontal line in the middle that schematically divides the real world from the computing world, where all the calculations take place. So these real-time measurements are used, are first entered into a data processing block where they may be enhanced or extended, and eventually all this real-time information is used to feed the control strategy block. And this control strategy block is the one that makes the decisions about how to drive the inputs of the process so that some pre-specified goals, for example, minimization of total time spent, can be achieved despite the impact of the disturbances that are in many cases completely unpredictable or only partly unpredictable. So in this figure, we have a technological part, the sensors, the communications, the computing devices, the actuators, which is the enabling skeleton of the system. And we have a methodological part, which is the data processing and control strategy blocks, which essentially reflect the intelligence of the system. Particularly the control strategy is something like the brain of the system, because it is the one that makes decisions, and if the decisions are not appropriate, of course, all technology will not be very helpful in improving the traffic flow process. So the technology is enabling, but the control strategy is the brain that makes the decisions that have to be the proper decisions. Now, what is the role of modeling in all this? We should say that traffic flow models are mathematical tools that imitate the process behavior. So in some sense, we could replace, ideally, the block of the process with a traffic flow model. Then if the traffic flow model is fed by the same disturbances, with the same disturbances and the same input control inputs, it should produce the same output as the real process. Now, traffic flow models are valuable for traffic control, because first we need to understand the behavior of the process if we want to design proper control strategies. In some cases, we may even have a model explicitly in the control strategy, like in model predictive control. And secondly, because we don't go with a freshly designed control strategy usually directly to the field, we usually would like to test it via simulation or test different concepts and see what seems to be best to be actually tested in the field. Now, I should say, however, that although modeling is valuable, perhaps it is sort of overestimated in the research and in the publication. So I think that if you make statistics, I never did that rigorously, but if you make statistics about how many modeling papers, how many control papers are published in various journals, then of course you will have a multiple of papers in the modeling area, whereas, as you understand, modeling is just a first step. And even if you could have a perfect model in any sense, that would by no means mark any direct improvement for the traffic flow process, because the traffic flow process can only improve by appropriate decisions. So to control congestion, we need definitely efficient control strategies. Now, let's leave the introduction and come to the first say, actuator or system that can be used to control freeways, which is RAM metering. You see on the photograph a 3-lane RAM metering, a 3-lane carriageway. This is in the south of Paris in France. And you see also to the right the on-ramp with queuing vehicles and the traffic lights barely visible, which control the traffic flow according to the mainline traffic conditions. So, how can such a system be designed? We will first talk about local RAM metering. Local RAM metering means that every ramp is controlled independently of all others, and by using measurements that are local, that are not far away from that ramp. So if we look at the left-hand diagram, you see schematically a mainstream with queuing, the upstream flow entering, and then a ramp flow R from the bottom. That's the ramp flow that needs to be determined. Our goal here is, if you look down at the fundamental diagram, our goal here is clearly to operate the system around the capacity. That red ellipses. So if we don't succeed in that, if we fall in congestion, we will have capacity drop, so we will fall down to the right part of the fundamental diagram. So if we look, there are two basic philosophies for local RAM metering. The first one is the left-hand side one, which is quite plausible. The point here is that we use measurements of queuing from upstream. You see it via the corresponding arrow that enters the strategy block. And then, assuming that we know the value of capacity downstream, we take the difference between the capacity value on one hand and the last measurement of inflow in real time on the other hand to calculate the appropriate ramp flow that should enter. Now, this is also known as the demand capacity strategy, but this strategy actually has a major deficiency. The deficiency is that it does not measure, it is blind to what it would like to control, because what we want to control is the downstream traffic conditions. This is what we want to control. We want to have capacity flow downstream, but in this scheme, there is no measurement from downstream. So that means that we act in a blind way. We don't see what happens. We are just open loop or feed forward. This is the reason why we developed an alternative strategy that you see on the right-hand side, which is called a linear. So in this strategy, what we measure is not the upstream flow, but it is the downstream traffic conditions. In this case, it is not the flow, because the flow, in case of congestion or free flow, can have the same value. It is indistinguishable. So what we measure is the occupancy, but this is actually nothing bad, because if you look at the fundamental diagram, we could say that our target, our set point, is now the critical occupancy. We want to operate the system around the critical occupancy, which is the same like operating it around capacity. So a linear is a so-called I-type regulator, is a feedback regulator, and feedback is something that is not or was not so much well known within traffic engineering, but I need to emphasize that you have feedback loops everywhere around you, in your computer, in your mobile phones, in your cars, in your appliances. Anywhere you look at, you have hundreds of feedback loops within any technological system that execute, different tasks. And feedback is something that in control engineering is the most basic thing and most efficient thing to address uncertainty, disturbances, and so on. So even in our body, nature invented feedback before us. So blood pressure and blood temperature and everything is done via feedback loops. So, I would need to talk much to a control engineer as to what are the advantages of feedback compared to open loop. Sometimes we have to do it in traffic engineering. Except for the feedback, there is an additional advantage of a linear over demand capacity, which is the fact that it turns out that the critical occupancy is much less sensitive than the capacity, the flow capacity value. I mean, there are many analyses by distinguished colleagues in the last years that indicate, based on real data, that indeed we have capacity values that can vary under the same environmental conditions quite strongly from day to day. And this is not so with the critical occupancy. Now, at the time this was developed, linear was developed, there were two extensive field comparisons with demand capacity, and they confirmed that indeed linear is far superior than the upstream measurement-based strategies due to the feedback nature, but also due to the issue that I mentioned here. An issue that needs to be mentioned here is that when you apply RAM metering, any strategy, then you should observe the ramp queue, because you don't want the ramp queue to become too long and possibly interfere with the upstream intersections, which would, of course, have a negative impact on the surface streets. And this is something we don't want to have. So we need to observe the queue. Now, we should say that in the last 20 years, any new RAM metering installation around the world outside of the United States, unfortunately, has been based on feedback-based measurements, and specifically a linear. Very surprisingly, there is still no single implementation of a linear in the United States, although all other countries have or have switched to feedback-based strategies. This is something strange, given also that there are brilliant control engineers in the United States. Here you see a sample of application of a linear, in this case in an implementation in Glasgow, where the set point in this case is 26%. That's the critical occupancy, and you see that the flow, the mainstream flow downstream of the ramp is the mainstream occupancy downstream of the ramp is maintained around the critical occupancy via the action of a linear. Now, there are many other, they're not really details, but there are many other peripheral problems that, and algorithms that should be considered to have better and more efficient results. I will not go into any detail regarding these. I will just emphasize again the ramp queue control issue. We don't allow ramps to grow longer than a pre-specified space. And this is important. If the queue reaches that, then we need to apply some ramp queue control, which essentially means that we disable the ramp metering in the form of a linear or any control strategy that is being applied. Now, we can have significant improvements in RAM metering if we can coordinate the RAMs. That means that we have a centralized system which receives the whole information, real-time information from the network, and decides about what should be done in each and every ramp. Why is this beneficial? So let's make a thought experiment. You see here the diagram of a freeway. The flow direction is from left to right. And you see that, let's assume that the last ramp on the right is the ramp that actually contributes the last drop, so that a congestion forms, and that congestion will, as we said before, without control, propagate upstream and will cover several other on-ramps and off-ramps. Now, what happens in this network if we apply independent alineas at each ramp? Well, then the very last ramp will activate its own alinea to avoid the congestion. That means that we will have a queue that forms on that ramp. That means that we will delay the onset of congestion as long as we have sufficient space on the ramp. But if the queue threatens to actually exit the limits set for that ramp, then we need to essentially deactivate ramp metering here, and that means that the congestion will form. Later, there will be an improvement, but it will form. And the other ramps, the other upstream ramps, will not do anything until the congestion, the mainstream congestion, reaches their domain, because they are independent from each other. So when the congestion reaches the second ramp, this will start working as well, will form a queue, but this is already a little late because we still suffer the capacity drop farther downstream, and all we can do is just to limit a little bit the extent of the ramp by doing that. So, as you see, and within this thought experiment, we can also conclude that the pain for improving the traffic conditions is essentially paid by the users of the downstream ramps, which is also bad for equity. Now, what would coordinated ramp metering do? Well, coordinated ramp metering could, for example, in this case, activate upstream ramps earlier, activate upstream ramps and maximize the amount of storage that is available to combat this further downstream congestion. In some way, we could say coordinated ramp metering should try in this situation to consider the whole available storage space as one single super ramp, rather than leave all the charge of addressing the congestion to the very last on-ramp. That would delay the onset of congestion much more, and in fact, in some cases, it might even lead to an avoidance altogether of the congestion. Now, how can we apply coordinated ramp metering? How can we design coordinated ramp metering? One way of doing that, which is a rather sophisticated way, is via nonlinear optimal control. So in this case, we define an optimal control problem where we consider explicitly the limited storage capacity and other constraints. We have a model in state space discrete time form, for example, METANET, that reflects the nonlinear flow dynamics, and we also have an objective criteria, which can be, for example, the total time spent. So such a problem can take huge dimensions, for a network of some size. It can include variables, hundreds of thousands of variables, but still there is a possibility to solve these in relatively minor CPU time, about 1 CPU minutes. There is a tool that we have developed called AMOC that solves this problem in a way that is invisible for the user. But what is most important is that such optimal control approaches, they have actually an inherent intelligence in the sense that they are able to tell us for specific scenarios, for specific network and demand scenarios, what are the most appropriate actions that one would apply. And I can assure you, by experience of myself and my group over several application domains, including freeway traffic control, that you can very often be surprised by the optimal solution proposed by optimal control, in the sense that you don't expect this kind of solution to be beneficial, let alone optimal, and then you have to analyze and try to understand why this result was produced, and eventually you come up with an explanation and you become wiser by a tool, a program, this is just a code, that you have developed, and this code teaches you what is optimal. So in that sense, you really have can have some inherent intelligence in this system. So let's see an example of application. What you see here is the ring road around Amsterdam. We only consider the counterclockwise direction. It's 32 kilometers long. It has 21 on-ramps and 20 off-ramps. And 4 of those on-ramps and 4 off-ramps are actually merging motorways. All the others are urban ramps. So you can see with red the motorways that are merging. So on the right bottom, you see A1, then farther left A2, then A4 on the left, and farther up A8. So these are merging motorways. And we can study the behavior of this network using a model for the afternoon peak, using a model like METANET mentioned earlier, which was validated with real data for this network, and actually the demands used for this simulation are also real demands, measured demands. So what we see here as the outcome of the simulation actually is pretty close or very close to the real conditions in this network. So what we see on the left diagram is density over space, that's the segments for the modeling, and over time, the time is about 4 hours. And what we see here is that there is, right at the start of the simulation, there is a congestion triggered at the merging of A1. You see just below where A1 is positioned. So you see a congestion triggered by the merging of A1 with the ring road, and this creates a congestion that propagates backwards and becomes stronger. Then there is a period of release of congestion a bit later, around the 2 hours from the start of the simulation. There is another congestion that is triggered at A1 merging, and this is much stronger and propagates backwards, and in fact covers half of the ring road. And this happened because this is some years ago. It may be worse or better now, I don't know. So this happened every afternoon. Now on the right hand side you see another three-dimensional diagram which reflects the queues at the on-ramp. So you see 21 on-ramps at the x-axis, then the y-axis again the time, and the z-axis are the queues at the on-ramps. And then you see some huge queues of over 1,200 vehicles. These are actually spillbacks of the congestion onto merging motorways, in this case A4. So in the simulation, but also in reality, the congestion that we saw on the left-hand side spills back and covers not only the half of the ring road, but it spills over also on A4 and extends for several kilometers on A4. Now we can play different games here, and you can use AMOC and say, okay, with the same density profile, the same demand and the same model, let's see what happens under different conditions. The first thing is to say, okay, let's apply RAM metering with queue constraints, but only for urban RAMs. So maximum allowed queue is 30 vehicles, and only urban RAMs are metered. The freeway-to-freeway RAMs are not metered. In that case, you have an improvement of TTS by 22%, which is, of course, seems very good, but we need to realize that that we are talking here about ideal conditions. We assume that we know exactly the demands and that the model is 100% accurate, which will not be the case, of course, in real implementations. Anyhow, if we look at the diagrams, the density, of course, it's less strong, but it's still there. And the queuing, you see now a lot of queues spread over different urban ramps, up to 30 vehicles, as our constraint has been, but there is still the spillback of congestion on A4. A4 has no RAM metering, but there is a spillover of congestion there. Now, we can tell what does it take to actually eliminate congestion and have a flat density profile. Well, it takes on the top of these urban RAM metering to also have freeway-to-freeway RAM metering with 200 vehicles storage space for each freeway, each of the 4 freeways. So if we do that, then we really eliminate virtually the congestion. You see that on the left-hand side of the diagram, and then on the right-hand side you see the queuing, which is according to the constraints. So the slightly higher queuing is only at the freeway-to-freeway ramps whenever it is needed. And the improvement is quite spectacular. In this case, about 50% of TTS reduction. Now, the point is that optimal control has many advantages, as I said, but is quite sophisticated, a bit heavy, and perhaps also not very easy to understand by the operators. So what about something that is sort of simpler, more transparent, easy to understand by the operators? That was the motivation for us to develop a coordinated strategy called HERO. And this one is based just on real-time measurements. There is no model incorporated in it. It is just feedback-based. And the idea is that you have independent alineas for every ramp. But then on the top of that, you have the logic of HERO, which essentially what it does, without going into details, is what I mentioned before. Upstream ramps try to get activated by HERO in order to assist the downstream active bottleneck ramp to address the congestion. Of course, there is a lot of things that are included in there, but the basic idea is this. And the first test, of course, of HERO was with the same model and the same demands as before. And as you can see, we can reach in this simulation 47% of improvement in TTS. But what is most important is that here, in this case, we don't have any model, we don't have any demand predictions. This improvement is based on the HERO strategy using only real-time measurements without any predictions, which means that it's much more robust than something that is produced by the help of a model and by the help of demand predictions. Now, when HERO was developed, we were very lucky to attract the interest of a very progressive authority, which is VACS, the authority of the state of Melbourne, of the state of Victoria in Australia. And we agreed to have a test pilot for HERO at 6 consecutive ramps, and that had a very big success, led to significant improvements in all performance indices that are being used by the authority. And in fact, the authority estimated the payback period to be about 11 days. And in this diagram, you can see the before and after situation, October 2007, October 2008. So every sub-diagram here is 1 day, actually the morning peak of 1 day. And so on the left, you see a lot of red, which is congestion. On the right-hand side, you see much less red. And of course, we don't see just green everywhere because we have just 6 ramps, and the storage space was not sufficient to completely eliminate congestion every day. But nevertheless, you see that there is a very obvious improvement. And after this, VACS decided to implement HERO on the whole freeway, M1 freeway, 75 kilometers in both directions, meanwhile more than 70 ramps, and also at other locations, and there are other installations and also planning and implementation phase for other networks for HERO. So let's now move to another actuator, like variable speed limits. You see here on the photograph an installation from the UK, so 50 here are 50 miles per hour. This was first introduced probably, there was also in the United States, but it was not automatic. I think in Germany was the first automatic systems in the late 60s, early 70s. Anyhow, the system became very popular, and you can see now variable speed limits around the world in many, many countries. I should say that the system is great for traffic safety because there are a few evaluations, year-long evaluations that I know of, which show that there's a reduction of accidents 20–30%, which is of course excellent. But in terms of efficiency, we have much less success. Actually, I don't know of any evaluation that would conclude on an improvement of travel times. Actually, there are several evaluations that indicate that there is a deterioration of an increase of travel times due to variable speed limits. And this is not, in my view, not due to the fact that variable speed limits are not efficient as such, but because they are used based on very simplistic lookup tables. That means the control strategies that are being used are simply not efficient enough, and there is a number of researchers in the area that are now working in this direction, trying to produce more efficient variable speed limit strategies. Now, these are results from a model fitting that we did using data from a European motorway. So you see here fundamental diagrams. The blue one is when you have no variable speed limit, and then if you take 60 miles per hour, then you have the pink curve, and then the green curve is for 50 miles per hour, and the black curve is 40 miles per hour. So in this case, and in that location, the fitting exercise based on real data indicated that you may have an increase of capacity due to homogenization of traffic. However, this is not consistent, and actually is not clear that this happens always and everywhere. For example, this was at another location of the same motorway where the change was not towards increased capacity for any variable speed limits. Of course, there are other significant changes. For example, you see the slope of these four diagrams at 0. They are decreasing with decreasing variable speed limits because this is the free speed. And so with driver's compliance, this is something that we should expect. Then we see the critical density shifting to the right, which is also something that one might expect. But you also see that at least after a certain value of variable speed limit, the capacity of the infrastructure is decreased. And if we extrapolate these also with variable speed limit values where we had no measurements, just extrapolate the formula, you can see that for even lower variable speed limits, you can get lower and lower and lower capacity. So we thought, let's see what our intelligent friend AMOC would say if we would tell it, if we would take the same scenario as before, but it would tell it that all you can do is to change the variable speed limits in this network. What would it tell? And we were very surprised to see an improvement of 47%, almost as much as optimal RAM metering, resulting from this exercise. And so we had to really look more carefully at what this guy was doing, and then we saw what the guy was doing was he was exploiting the reduced capacity of fundamental diagrams when I apply variable speed limits in order to apply mainline metering, mainstream metering, upstream of the main active bottleneck of this freeway. That means upstream of A1. So we called this MTFC. It is an error, not motorway traffic flow control, but mainstream traffic flow control, enabled by variable speed limits. And this is what was leading to this improvement. And in fact, after seeing that, we thought, okay, I mean, optimal control has some disadvantages that I mentioned before. So let's try the same thing with feedback. So you see in this diagram that we can take measurements from detectors and then apply a similar feedback control algorithm like a linear, but now it is applied to a different actuator, which is variable speed limits. For example, in case you have two main motorways merging, you want to maximize the throughput at the downstream. Then if you don't want to use traffic lights, you can use variable speed limits on one branch or on the other branch or on both branches. And in this case of both branches, you have an additional degree of freedom that you can use, for example, to have equal delays on both branches. And of course, the main thing here is that always that we want to maximize the throughput at the detector location. The same can be done also with regular on-ramps. And this actually can be generalized. We can have generally bottleneck throughput maximization, not just for on-ramp merging and motorway merging, but for other merging cases like toll plazas, motorway work zones, mainstream lane drops, but also other types of bottlenecks like weaving sections. We can apply that upstream of weaving sections to maximize the throughput, or other kinds of bottlenecks like sags or curves or tunnels or bridges. So all that, all those bottlenecks which produce a capacity drop when you have a congestion can be addressed with these tools. And the idea is the same. We want to apply feedback control. We take a measurement or an estimation from the merge area in case of a merge bottleneck, or from the congestion area in the case of other bottlenecks, and then we feed that to a control algorithm that controls the inflow by use of actuators like traffic lights or variable speed limits. So this is the case of application for a toll plaza, in this case San Francisco Oakland Bay Bridge, where you go from 15 lanes upstream to 5 lanes on the bridge freeway. And of course, you have the corresponding, after passing the toll booths, you have the corresponding merging area. And you see here what should be a microscopic simulation, but we don't have the possibility in this system to have it moving. But you can imagine that when the inflow is higher than the outflow capacity, then you will have something like that in the merging area, and all these merging conflicts and accelerations of vehicles lead to a drop of the outflow. Now, it is clear the drop of the outflow is due to too many vehicles being included in this merging area. If we would have too few vehicles in the merging area, then the outflow would starve for flow. So too many is not good, too few is not good. Somewhere between the two, there must be some magic ideal number of vehicles in the merge area that produces the maximum throughput. And this is exactly what we can do with feedback control. This is the case with control. Now you see on the left side those red and green bars, which are traffic lights. And the idea here is that you take a measurement from the merge area, feed it back, control the traffic lights, and the goal is to maintain the number of vehicles in the merge area as close as possible to the number of 20, which produces the maximum outflow. And that's all. Then you can improve your outflow by 10–15% in this case, because you avoid the merging, the congestion in the merging area. Similar for work zone control, we don't need to repeat that, corresponding simulation. Now, I hope you are not too tired, so that we have a few more minutes to talk about the future of motorway traffic and control, which has actually started in the sense that we have already vehicles with advanced cruise control on our streets and several other systems on our streets. So if you recall the basic elements of a control system that we had in the introduction, the process was conventional vehicle flow. The sensors were spot sensors like loops, vision, magnetometers, and so on. Communications usually wired, and computing usually either central or hierarchical, in some cases decentralized. And the actuators are roadside, RAM metering, variable speed limit, variable message signs, and so on. Now, what comes in the future, and is partially already there, are quite strong differences. The process will be now consisting of vehicles that have enhanced capabilities. ACC, for example, means that you can forget about all car following behaviors of drivers, because now the system does it. So this influences the traffic flow. The sensors can now be vehicle-based. If the vehicles can communicate with other vehicles and with the control center, then you can have massively data from vehicles about a lot of things that you did not even dare to think about before. Communications will be mostly wireless, V2V, vehicle to vehicle, vehicle to infrastructure, infrastructure to vehicle. Computing, again, it can be central, decentralized, or hierarchical, but now you have the possibility to have it massively decentralized in the sense that a lot of things can happen within the cars. So you can have parts of the control strategy, and some people even dream of having the whole control strategy in the cars, decentralized. And of course, you have in-vehicle actuators, because now you can tell vehicles what to do in terms of routing, in terms of speeding vehicles, in terms of speeds that they were going to use, in terms of lane changing and so on. So this opens up a whole new area of investigations, needed investigations, in order to study the implications of these systems for the traffic flow, and then, of course, exploit them for a better traffic flow efficiency. The main developments, which we sometimes call VACS, Vehicle Automation Communication Systems, can be classified in three categories. So we have the in-vehicle systems, sometimes called automatic vehicles or advanced driver assistance systems. The vast majority of these systems are related to safety and convenience of the driver, which is good, but there are some few that have direct traffic flow implications. And so these are the ones that we need to focus upon. Under a different viewpoint, we talk about vehicle infrastructure integration, VII, or cooperative systems, or connected vehicles. And this is when vehicles actually can talk to each other and with the infrastructure and exchange messages. And then under a different viewpoint, again, we have platooning, various versions of platooning in our streets, which probably will require also corresponding changes in the infrastructure. So the basic point to keep here is that intelligent vehicles may lead to damped traffic flow. There are specific examples that I could tell where having this intelligence in the vehicles is detrimental to the traffic flow. So we can, in fact, make things worse if there are sufficient intelligent vehicles on our streets. When? If not managed appropriately. So we need to continue with freeway traffic control, traffic management in parallel to those developments of VACS that are ongoing, emerging, and some of them are already on our streets. So what needs to be done? We need new modeling approaches and tools, both microscopic and microscopic. We need new simulators. Some of them are already, a lot of colleagues have worked in that, and some of them are already around. We need to ask which conventional traffic control techniques can be taken over in the future. But most importantly, what new opportunities are appearing with all these new data that we will have, new actuators, new communication channels, and so on. And how can all these be exploited for more efficient traffic control? So these are very important questions. We are very glad and proud that we have received a so-called ERC Advanced Investigator Grant. ERC stands for European Research Council. The name is Tramon 21, stands for Traffic Management for the 21st Century, where we address exactly the kind of questions that I just mentioned for motorways. And you see here the website of the project if you are interested to get more information. It has started this year, so we are not very advanced yet, but I hope we are on a good way. So there are many challenges here. The system now is very large scale because there are so many cars that have, you know, an identity in the system as sensors or as actuators. They are not just particles of the flow. The evolution path is uncertain. We don't know which of those VACS will actually appear on the streets and in what order and so on. There will be certainly a gradual penetration. So that's also something that may cause difficulties because, you know, we need to have tools that will be applicable under different penetration rates. And there are many other issues that are not within our domain, like the deployment scenarios, security issues, liability issues, insurance, legal aspects, standardization, but also human factors. I mean, these things need to be accepted by drivers, and this is very important. It's not, you know, our work, but it's very important that these are accepted by drivers. Otherwise, you know, I mean, they will not actually appear on our streets. So I hope you are not too tired. I come to the conclusions. First of all, I believe that motorway traffic flow can be substantially improved even with conventional means right now. We don't need to wait for the future. And improvements in some cases can be as far as 50% of travel times. We need more efficient and practical control strategies. Of course, we need more installations of potentially efficient control tools. So we need to really go to the field. This is something that researchers have to take into account. It is much more convenient and rewarding for publications to work based on simulation, but you know, our work theoretically is about improving the real traffic flow. This is what we need to do. And finally, what regards the future, traffic control continues to be vital for reasons that I tried to present, while all these VACS are emerging. So that was the end of the presentation. Thank you very much for your attention.
Thank you so much, Markos. That was a great presentation. I learned a lot. I would like to ask the participants, so if you have any question, you can write in the chat box, and Markos will read them and he will answer your questions. Thank you again, and if you have any question, please write in the chat box. Oh, Bahar, yes. You asked, are you circulating the presentation? Yes. There is. I have a link. Here is a link. I'm gonna paste it in the chat box. Here is a link to the list of the webinars we have already hold. So the link to the recorded webinar and and Markos' slides will be there. So if you couldn't watch, or if you want to let everyone else watch it again, feel free to distribute that among yourselves. So there is a question from Lokesh that asked, doesn't that, oh, hold on, let me go one more up here. Okay. How about a dedicated lane to heavy vehicles? Doesn't that make cars move much faster?
Yes. Well, a dedicated lane can be there for various reasons. Everybody knows HOV. I hear my voice coming back. I have a return.
Let me mute. No, let me mute myself. Sorry.
Yeah. So dedicated lanes can be used for many things, like HOV or, as you say, heavy vehicles and more. The point is always that we need to assess beforehand whether this is going to improve or possibly deteriorate things. And it all depends, of course, on the corresponding demand, which may be different at different times of the day. And of course, we had recently with some colleagues from Spain work, for example, for reversible lanes, which is similar in the sense that if you apply reversible lane in real time, then you know, you need to take into account exactly the demand from one or the other direction, when it is actually reasonable to open the reversible lane, to what direction. I would imagine that dedicated lane is something that would be decided, if it is assessed to be beneficial, based on time of the day or as a permanent measure, rather than a real-time control action like the ones that I presented here.
The other question from Bahar is, can you give an example when vehicle automation degrades capacity?
Yes, you know, if you take an ACC vehicle, the recommended time gap is 2 seconds. So if you have everywhere vehicles with a time gap for 2 seconds, your flow capacity will be maybe 1400 or something like that. So that's one example.
The other question from Vincent is, could you please explain why intelligent vehicles can lead to dumb traffic flow?
Yeah, this is similar to this one. I gave one example. Let's give another example, just since there is a second question. For example, in in route guidance, if you have just the kind of information, real-time information given to vehicles that you have now, but you have a high penetration of vehicles receiving this information, then you may well lead to a deterioration of the traffic conditions in the network. This is something where several colleagues in the past, also your supervisor may have worked and have shown that as the penetration rate of vehicles receiving this information increases, you have to take into account in your feedback or in your predictions their reaction. Otherwise, you may end up worse than without providing the information. So that's another example, and there are several others.
Yep, and I have a question as well. We've talked a lot about freeway traffic control. So whatever strategy we implement, as long as the demand is the same, the congestion will spread either on the ramps or upstream of the freeway. Do you think mixing freeways and arterials, I mean, having a combined control strategy of arterials and freeway might be needed in future because, as I said, the congestion would spread, probably would propagate into arterials close to the freeway. I think there's also a need for looking at the combined arterial and freeway.
Yes. First of all, yes, the congestion, as you said, will spread, but we should not think that this would mean that you have the same amount of congestion just at different locations. The most crucial point is that the uncontrolled congestion degrades the infrastructure. That means reduces the outflows from the system. You know, when every vehicle that is out of the system is out of the system, and you don't have it in the system as contributing to the congestion. So the point is with control, not just to spread the congestion, but to spread and reduce it, and more specifically to enable an increase of outflows so that the excess demand, excess to capacity, will be less than with blocked exits or with reduced exit flows. Now, regarding your actual question, absolutely, I agree completely. The network is an entity. We don't just have freeways for some people and arterials for other people. The same people may use both. They have actually the choice many times. They make a choice. So it's an entity, and we should look at the whole system. The point is that it is probably very complex. There have been many attempts. My group has worked in that. Many other groups have worked in what Bayer group has worked in corridor control, as it is usually called, systems. It is very important, but, I mean, as long as we are not sufficiently efficient for motorway traffic, or on the other side, sufficiently efficient for signal control. We didn't talk about signal control, but there are also a lot of problems with saturated traffic. Let alone if you put both together, that becomes even more complex. So I suppose, there are some research results, but I don't know of any system that would be really very efficient for the whole corridor network in some, systematic scientific way. In the field.
Yep, thanks. There's also a question from Rudy. He said, for VSL, if the lower the speed, have you observed increased density in the field? If so, do you think this would make lane changes more difficult?
First of all, unfortunately, we don't have any field implementation of the VSL concept that I mentioned in the field. Within the project Stramon 21 that I mentioned, there is provision for field trials that will test this, and then I will be able to answer your question at least as far as the field results are concerned. Now, usually the variable speed limits are thought to reduce the need for lane changes because, I mean, with a reasonable compliance of the drivers, if you have the same speed on all lanes, there is no incentive or less incentive for a driver to change lanes, at least in order to advance faster. Now, of course, if you would like to exit at an off-ramp or take another route, that would be something different. So I think that variable speed limits in general, and with higher density in particular also, would probably reduce the need for lane changes.
There's a question from Arash, which I think you answered previously, about why ACC V2V V2I may harm more than good if not managed properly. I guess it's the same as the first two questions. So the next question is, what is your view on controlling the traffic flow on freeway when the system has mixed traffic, conventional vehicles and intelligent together?
Yes, this is a very interesting question. There are already some works in this direction. I mean, there are some colleagues who started working on this before us. We just started with this new project, and there are several results. And I mean, it all depends, as I mentioned before, on how the automated or connected vehicles will behave compared to the other vehicles. There are several, of course, simulation-based evaluations. We don't have enough vehicles to do field experiments, which indicate that there is a potential for improvement if these systems are managed properly, but there is also a potential, as I was mentioning, for deterioration if we just let car manufacturers and drivers do whatever they want for their safety and convenience and don't take care of the resulting traffic flow features.
Okay, great. I guess we are done with questions. Thank you again, Markos, for your time and the presentation. If you let me, I would put the slides online so people can look at it.
Absolutely, yes.
And the webinar is recorded, so I will include the link on the Facebook page on the list of the traffic flow webinars so everyone can watch it again. Thank you everyone for joining us, and thank you again, Markos, for your time and the great presentation.
Thank you, Mehad, and thank you everybody who attended.
Yes, have a great day, everyone. Bye.
Bye-bye.